Here we are, chapter 26. This is one last video for you guys for the semester. So, good luck on the final exam. Should be available to you now. And this is for your own edification. There's no homework on this section. All right. We have actually talked about group presentations and use that notation actually, but maybe not that terminology before in the class, actually, all semester really. But here I'm going to formally define what it means for more than one element of a group to be a generator, and what it means to have generators and relations that define a group. So first things first, I'm going to talk about the formal way that we create elements from a group from a generating set. So we take S to be a set of symbols, and S inverse are all those symbols with little negative ones of as a superscript. In other words, those are the inverses. Then we can define what's called the set of words. It is very much not countable, okay? Because I don't know if you've seen the definition or the proof that all binary strings, so strings of zeros and ones, that's not countable for the same reason that the real numbers are not countable. I mean, you can define all real numbers as binary strings using binary counting or binary numbering systems. So this is a huge set, right? So we just have one generator. What we would get here would be something along the lines of the integers, if we were allowed to add equivalence between words. Okay, and I'll show you that in a minute. So anyway, there's also a identity element on this set of words. It's the word that doesn't have anything in it. Okay, why is that the identity? Well, because we're going to define a operation on the set of words by juxtaposition. So x1 times x2 is just x1 then x2, right? Where x1 and x2 can be any collection of these symbols. Okay. So we can say that two words are equivalent if you can insert or delete a word next to its inverse, or its inverse next to that same word, which is basically just multiplying by the identity, or adding the identity to any, or the empty word to any position inside a word. That creates an equivalence. So for instance, here's an example. Say I've got word 1 is BA, B inverse B inverse B, C, D. Okay, that's going to be equivalent to something like B, A inverse A. See how I've just put that in there. B, -1, B, -1, B, C, D. Well, now I could have removed this one here. So say I just remove that. So I'm going to remove this thing here and just have CD. So anyway, These two words are going to be equivalent in the set of words on the set AB. Okay, so ABCD, sorry, CD. Okay, so how do we can create a group that way. Now, generally speaking, it's quite difficult to decide when two words are equal according to this equivalence relation. Maybe I need to show it's an equivalence relation, but it definitely is. But I'll talk about that a little later. So, it is really hard sometimes, and by hard I mean not algorithmic, hard in the vein of computer computational complexity, to decide in a general setting when two words are equivalent. Okay, this is called the word problem. Not a word problem, the word problem. And so that's just an aside, I guess. I'll talk about this maybe at the end of the section, or at the end of the video today. And there's a lot to read on it. But let me just show right quick that this is an equivalence relation. So well, how do you show two things are equivalent, or that comparison between two algebraic objects defines an equivalence relation? One is reflexivity. In other words, is the same word equal to the same word? Well, that's definitely true, right? I don't have to add or remove anything from W1 to be still W1. I need to show that if that is true, so then not reflexivity, but I forget what that's called. Switch it around. I've lost my train of thought. Anyway, if one is equivalent to the other one, you should be able to switch it and say that they are the same. Yes, if you can get from W1 to W2 by a string, by inserting or deleting things of the form x inverse, or x inverse x, okay, then you can just reverse the process to get from W2 to W1. So if sequence exists to go from W1 to W2, then reverse the order to go W2 to W1. Okay, so that worked out. Lastly, transitivity. W1 is the same as W2, and W2 is equivalent to W3. Then W1 is equivalent to W3, and that's definitely true because if you have a sequence from W1 to W2, and then from W2 to W3, then you just do the sequence one after another to get from W1 to W3. W1 to W2 and W2 to W3 definitely implies W1 goes to W3. Okay, so it's a, I don't know if I need to show that. Anyway, here's a theorem. We have a well-defined equivalence of words, and if that's all we set as to determine difference between elements in this set, what we can do is add a multiplication called juxtaposition, and that defines a group called the free group. Okay. Also, f of s is sometimes free group, but also our familiar angle brackets. Proof is very easy, so there's definitely an identity, right? So E equals the identity. Since if you take an empty word and juxtapose it to the empty word, right, you still get the same word, right? And backwards as well. Okay, so there's an identity. Let's see. Oh, that's number 2. That should be number 2. Group axiom 1 is associativity, right? So is associativity, is this true? Well, yeah, definitely. There's really nothing to show, right? Last one, inverses, okay? So if W1 is like x1, x2, up to xk, right, then that is by the shirt and pants principle, or whatever we called it, shoes and socks principle. Take them reverse order with inverses up there, and you get the inverse. So if I do W1 times W1 inverse, this is x1, x2, x3, up to xk times, or next to the thing, but we're in reverse order, and all of those guys will, by associativity, will cancel out one at a time, right? Now the question would be, okay, well, what if you have an infinite word? Well, the set of words are finite length. Okay. It is possible that your generating set could be infinite, and your words could be approaching infinitely long, but any given word is finite length. Now, here's a theorem that really comes from another theorem. This is really a corollary to a theorem in your textbook called the universal mapping property. But essentially, this says that we can write every group in terms of as a factor group of some free group. Okay. And that will later mean that there's always a way to write the group in terms of generators and relations. you have enough time anyway. Could be quite complicated. But so the first things first, I want to find a free group on some generating set that will map to our given group. So let's let G be a group. Let S be a generating set for G. So this means that every element in G is some word in elements from S. So S is a subset of G, but we know that it exists since if you let G be all of S, and we know that every element in G is some finite word in of elements of S. All the words would have to be length would only have to be length 1, right? But and here I'm using multiplication or multiplicative notation for G, or I'm going to, but of course addition, additive notation would work also. So maybe I should have said something like that before, but x1, x2, x3 as a word, right, is in multiplicative notation, like x inverse x1 minus x2 plus x3 is in additive notation, right? So the more general case is the multiplicative notation, so I'm going to use that. All right, so then there's a generating set for G called S. So that means I can form a mapping from the free group on S, also known as bracket S, to G, where I take a word in S, okay, and I'm just map it to the word in G, whatever that group element turns out to be, okay? Really not that weird, but I am sort of abusing notation here. And there's a discussion about the abuse of notation in your textbook when they prove this universal mapping property, but I don't think it's necessary. You take something in the free group on S, right? It will be some formal list of elements from G, right? Of course, S is a subset of G. Maybe I should say that. S, subset of G, okay? But, you know, there's certainly more than, this isn't a unique way to represent elements of G, but I don't need this to be one-to-one, okay? This just needs to be onto and operation preserving. So here phi is a homomorphism since W1, W2 maps to W1, W2, right? Here we're just using juxtaposition, right, as our multiplication, but here this is the multiplication in G. It doesn't really matter, right? This is still going to be phi of W1, phi of W2, then so this means that phi of W1, W2 is indeed what you get when you juxtapose or multiply in G the images of those same words. Okay, so it's definitely a homomorphism. That's pretty clear. Is it onto? Well, definitely, right? I mean, if G is in G, right, then G is some collection of elements juxtaposed to get together by the multiplication in G, right? Where those are taken from S and S or S inverse, right? That's what it means to be a generating set. So that means, G is a word in the free group maps to G, right? So that makes it onto. All right. So who cares, right? But this is, once again, another application of the first isomorphism theorem. It implies that the image of our mapping, our homomorphism, right, is G, all right, that's the image. That's going to be isomorphic to the domain modulo whatever the kernel is, right? So that means G is isomorphic to the factor group of some free group. Okay. And so we say that G is isomorphic to a factor group of a free group, but here I'm going to let N be the smallest normal subgroup that lives inside the free group that contains some generating set, or in some sense, of the subgroup N. Okay? So in other words, take the kernel, right, and figure out what its components are. Find the smallest normal subgroup that contains all those elements in the kernel. Right? That would be N, equal to the kernel, right? If that's the case, then we can find a hopefully finite set of words that we're going to call relations. And we define then G to be generated by this generating set, A1 to AM, with relations, W1 to Wn, right? These are just new ways to take words in the free group on the generating set A1 through AN. Okay, A1 through AM, right? These are words, right? So the only relations that you have in the free group is if you have one word next to its inverse, then that's the identity. But here, there's other ways to reduce words, okay? And if we have a finite list of generators and a finite list of relations, we call this a finite presentation or a group presentation of G. Okay, and here's some quick examples for you. So the first one, Z, this is kind of silly. So this is the free group on a single generator, right? We've already seen this. We've already used this notation, okay? So that is, it's got the generating set A, but no relations, okay? What about Z mod N? So another way we could call that is Z mod NZ, right? Factor group of the integers. That would be generated by a single generator with the relation that A to the N is the identity. Right? What about external direct product of Z's? Well, this has two generators, right? But it's not the free group, right? There actually is a relation here, and that would be that AB, that would be that it's an abelian group, okay? It's the abelianization of the free group on two generators, right? So the free group here on the set AB is not equal to this. It's pretty weird. This is sometimes denoted by Z star Z, okay? I don't think we use this notation in our textbook, but it's a really interesting thing here. In algebraic topology, we see this a lot when we look at fundamental groups of interesting, of certain one-dimensional loops. So, I don't know, that's for another day. Okay, what about dihedral group? I've already written this before, so we've got S and R, okay, such that S squared equals R to the N equals SR squared equals the identity. So that turns out to be the group presentation for the dihedral group, and we've seen this a lot, okay? What about Z mod N plus Z mod M? We could write this as AB such that A, B, A inverse, B inverse. So that basically shows that you can, it's abelian, right? That just means AB equals BA. You solve for both sides for the identity. But what about this? A to the N and B to the M. Okay. And, you know, there's a bunch of other examples in your text. One last thing I wanted to talk about was this word problem thing. Just because you can't find a sequence of insertions or deletions from the set of relations to take one element from a group and show that it's equal to another element in a group with a finite presentation doesn't mean that it doesn't exist. Okay, so generalized word problem is that there are algorithms for some groups. Okay, finite groups, it's easy to see that you can use an algorithm to show that G1 is G2. You can just compare. Is G1 equal to this one? No. Is it that one? No, no, no. You have a finite thing. So that there's an algorithm for that. So the word problem is easy for a finite group. For free groups, okay, finding whether a one word in the free group is equal to another word, that's algorithmic too. You can take all instances of the juxtaposition of a word with its inverse next to each other and just get rid of all of them and reduce the words to their minimum length. That would be an algorithm for free groups. But if you take more relations, then actually gets more difficult. There are groups that are undecidable. They end up being infinite groups, and they have a weird presentations. Some of them are easy to write down, you know, if you had enough time or took that effort. One of the first and coolest theorems on the word problem was it done by Dane in 1911, showed the fundamental groups of closed surfaces have solvable word problems, and they are very complicated groups, but they have a nice presentation. Anyway, here's an example of a generating set for, let's take a surface that looks like this. So it's like the interior of this, to make it a surface, it means it's two-dimensional. So it's just the boundary of this, I don't know, like donut shape here, with these are holes. These are meant to be holes. Okay? And if you take loops, remember what the fundamental group is. These are loops that go from one base point, from wherever the base point is, to itself. I'm gonna let the base point part, I'm gonna let it wander a little bit, because this whole thing is path connected, so there's a way to get from here to the base point, say the base point's there, and back no matter what. But anyway, if you take the loops that go around the meridians and the loops around the longitudes, okay, this constitutes a generating set. And there's a presentation that, if you wanted to take my topology class, I'll talk about that. But it's definitely my not theory class, I would tell you about that. But there's a way to look at relations between these guys. Okay. Turns out that those have solvable word problems. So if you take any two elements in the group, that is, any times around this one and then that one, and you did another one in a different order maybe, and you want to decide whether those two things were equal under the relations of the fundamental group of this surface. Apparently you can do that with a polynomial time. Okay, but there are a lot of groups in which that's not possible. All right. So that's where I'm going to stop. Thanks all, and see you around the virtual superhighway.